Okay, hi everyone. Thank you for coming. It's a pleasure to have our very own young Grebik will tell us about local problems on grid.
Okay, so thank you. So I would like to thank the organizers for giving me this opportunity to speak about our results with Warwick. And in this talk, I will talk about grids and local problems on grids. So this is a part of like a bigger research program. And so what is this research program about? So what are the local problems? So very often it happens when you try to solve some very particular problem that the combinatorial core can be equivalently stated by finding some labeling of some graph that satisfies some configuration. So for example, if you want to do this circle squaring or this Banach-Tarski paradox, you just start with circle or square, and then you basically translate the problem into finding a perfect matching on some graph. So this is and perfect matching is a local problem because you can locally in one neighborhood of each vertex check whether it is matched to someone and whether it's matched exactly to one vertex in its neighborhood. So this is like the motivation. So and what is the local approach to these problems? Where very often you need that this labeling or coloring satisfies some regularity properties, and in different area this means different things. But very often again, it just means that a vertex would like to make a decision to color itself. And the vertex, and we only want or demand that the vertex knows just a small part of the graph around itself, and depend on this local statistic around or a local neighborhood around it, it will output some color. So and because this is really like a phenomenon that can be found in several areas. The general problem is if there is some translation between the results. So for example, if we know that in distributed computing, we can find an effective algorithm to 3 color some particular graph, does it mean that there is some factor of IID that also does it? Okay. In this talk, I will only consider these 2 settings, so distributed computing and random processes. And also, I will define the notions from random processes basically with the language of distributed computing. Okay. And also, as I said, this talk is about grids. So in the finite setting, we talk about d-dimensional torus, and it has side length like d root of n, if it has size n. And in the infinite setting, we just have this one z to the d d-dimensional oriented grid. So orientation is not that important, but just to make sure, because all the result that I will state is for oriented grid. So some of them can be stated for a non-oriented grid, but maybe there are some small problems when you try to work without orientation. Okay, and also what I will say is like now in some kind of unified language mixture of results from distributed computing of Brandt et al. So this is a paper that has like 10 authors. So I think it's from 2017. And so this is from distributed computing. And then this paper of Holroyd, Sharma, and Wilson is from random processes. And they basically, yeah, so they investigated like finitary factors of IID. And then we have a paper with Warwick, and there we try to like unify the notions and put everything in the same context and explain the similarities. And so in this talk, I want to just illustrate the connections. So maybe I will sometimes not precisely say who proved what, but I just want you to have like some kind of picture what you can get when you study this connection between distributed computing and random processes. Okay, so let me start with the main definition. So the main definition is what is a local problem, because we will find these connections when we will study complexity of local problems. So local problems are all the standard combinatorial problems that you know. So it's like a coloring, proper coloring, k distance independent set, or maximal k distance independent set, edge colorings, edge orientations, or maybe tilings, perfect matching. So these are all problems when, if I give you a solution, like candidate solution to that problem, you can locally around each vertex check whether some local constraint is satisfied. And if it is satisfied everywhere, it will be a valid solution. So the formal definition, so the original definition is also with like inputs, so that the graph can have some input labeling, and then you want to find an output labeling such that together these two labels satisfy some constraints. So let's make it simple. So let's not talk about input labelings. So what is a locally checkable labeling problem? So I will from now on denote it as LCL. So you have some alphabet, some sigma, and then you have some locality of the problem, which is some positive integer t. And now P is a collection of all rooted sigma labeled graphs up to isomorphism that have diameter at most t. So it's some subset. So basically this is the set of constraints around vertex. And now correct solution. So you label vertices of your graph. And now correct solution is if around each vertex you satisfy the local constraints given by this set P. So you can define this for any class of graphs, but here, of course, I only define it for grids or for rooted grids. And then this labelings, I consider that this graph G is a torus or infinite grid. So also this is one thing that it's like it doesn't matter. This definition applies to infinite or finite graphs. Like maybe what you require is that the locality of the problem, this number t, is much smaller than this dth root of n, so that you consider a bit large enough to write, so that it makes sense. Okay, so I hope this is clear. So this is the main definition of local problems. And now I want to define what is the local model and randomized local model. So I will not define what is deterministic local model, so randomized. So what is the traditional definition that Vasek always uses? So you have a graph G, and you want to solve some LCL problem. So you view G as like a network of computers, and so vertices are computers, edges are communication links. And then like each computer runs the same algorithm, but computers are allowed to exchange messages. So in parallel, they run the algorithm, then they exchange like unlimited size messages, and then they run the algorithm again, but now based on this more information that they got from the neighbors, etc., etc. And now you say that like the complexity of your algorithm is t. If after t many rounds you are ready to output the solution to your LCL problem. Okay, so of course you say that this algorithm solves the problem if what you get is this pi coloring, so the constraints are satisfied. Okay, so there is this one thing that if I define it like this, and we work on transitive graphs where each vertex is the same, looks the same, then of course, since the algorithm at each vertex is the same, we cannot compute anything. So we need to break symmetries. And so the traditional way, or there are two ways. The one is that deterministic and one is randomized. So let's just briefly mention that deterministic means that every vertex is assigned some unique identifier from some range. If the graph has size n, you can think that there is some bijection between vertices and the set 1, 2 up to n. But in the randomized setting, each node generates a sequence of random bits. And like for simplicity, let's assume that it's infinite sequence, but it can be arbitrarily let's assume it's infinite, but normally how we would define it is that we would say that there is a large number m, and each vertex generates m random bits. Okay, so if you have infinite sequences, then with probability 1 you will break all symmetries if the graph is finite or infinite. And now if you run the same algorithm so that you just the vertices t times exchange messages, now they can of course send the information about the random bits. So what the algorithm actually does is that if it has complexity t, is that it scans the t hop neighborhood. So every vertex scans gets know his t hop neighborhood with all the assigned random bits, and then depending on this, it will output some color. Okay, so formally, randomized local algorithm is nothing else than just a map from some rooted grid graphs that are labeled with infinite sequences of zeros and ones. And the range of this map is this finite alphabet sigma, when this is the alphabet that when we try to solve some LCL problem, and this is the corresponding alphabet. Okay. And we also say that if we have a graph and some number t, then the output of algorithm A on G after t rounds is some function that is defined, as I said earlier, so that you take a vertex V. This vertex scans the t hop neighborhood, and then it will basically put this as an input of this function A, and it will output some symbol from sigma. So you do it for every vertex, and this is how a randomized local algorithm A produces in t rounds some coloring. Okay. And now we say that A solves LCL problem on G in t rounds if with some probability that depends on the size of the graph, the outcome will be this pi coloring. Because what can happen is, for example, that with probability 0 you assign like the same random sequence of random bits to neighboring vertices, and then this algorithm will not output the correct solution. So you cannot say it will always give you the correct pi coloring. And you also say, you actually say that it can have error with probability 1 over the size of the graph. So at least 1 minus 1 over G. That's what should be here. Yes. So here should be 1 minus this quantity. Okay. Okay. So this is like a definition of what is the basic object people study. So randomized local algorithm. So you assign random bits to your vertices, and then you have some locality. Then you have some number t. So this t is different from the locality of the problem, and then this algorithm just computes locally some element from sigma, and you require this to be with probability at least 1 minus 1 over the size of the graph correct solution. Okay. And how do you measure the complexity? Well, for each n, there will be some number tn. Okay, so this is some problem, some LCL problem. So it has locality t, but now you require different tn. So I should have named it Rn or something. Sorry. This locality now depends on the size of the graph G. Now if you give me a graph of size n, let's say, then you apply this local algorithm A that you assume exists on this graph G with locality Tn. Okay, and now you require that it will always give you with probability at least 1 minus 1 over size of G correct solution. Okay. Okay, so like one thing is that that this Tn, they depend on the size of G, and so basically this is like the sequence of the algorithm. Basically, you can think of A as a sequence of algorithms. For each n, you have a different algorithm, and this algorithm operates only on graphs of size n. Okay, so this is like the crucial difference between this approach from random processes and from distributed computing. That in this definition, for each n, you have basically a different algorithm that operates on graphs of size n. Okay. So this is the complexity, and now like few examples. So, for example, assume that you would like to try to construct a two-coloring or perfect matching of a finite torus. So then this problem is not solvable because your torus can have odd size, right? Or it can have odd cycles. So then you cannot have two-coloring or perfect matching. So this problem cannot be solvable by any randomized local algorithm. So okay, so we can ask about the three-coloring. So then there is some argument that this also like when you say global, what does it mean? That means that vertices, they have to see the whole torus, like that it's actually not local. So if you would like to try to solve three-coloring, then the vertices needs to see the whole torus. So they have to look at the diameter at least dth root of n. Okay, so there is some algorithm, some argument that you cannot produce a three-coloring with local algorithms. And then this original algorithm by lineal tells you that you can actually produce a 2D plus 1 coloring when D is the dimension of the torus. And so this is a very important complexity, this log star n. So this will appear very often. So log star is just iterated logarithm. So like how many times you have to apply logarithm to a number n so that the output will be below number 1. So it's like an inverse of this tower exponential function. So it grows very slowly. So lineal come up with an algorithm that works for any graph of degree bounded by some number delta that you can delta plus 1 color it. So this corresponds to this greedy upper bound on chromatic number. Okay, so it also applies to grids, and in grids you have degree 2D, so 2D plus 1 is enough. Okay, but actually on grids you can find the 4 coloring. So there is some grid specific argument. Is independent of the dimension, and you can find 4 coloring in this complexity log star n. So on the next slide, I will actually show you that this is the only complexity that makes sense from the point of view of distributed computing. Okay, and like, what would it mean if there is actually an algorithm that solves a problem pi, and its complexity is just a constant? So this sequence Tn, it doesn't grow at all. It's just some like fixed number, like 17 or I don't know, 1 million. Well, then you can prove that actually the complexity is basically 0 because there is one fixed color in your alphabet sigma, such that when you color only with this color alpha, then you will obtain a valid solution. So such a problem, we call them trivial because they are trivial, right? So yeah, so basically these are the three important classes, like problems that you have to see the whole grid, like 3 coloring, or maybe even problems that cannot be solved, like 2 coloring. And then this log star n problems, which is like the greedy coloring, the greedy upper bound. And then there are trivial problems when actually there is like a constant coloring is okay for some color alpha. And now, so like if you combine work of a lot of people, so so I didn't put any reference here because it's a lot of papers. Then there is actually classification, like of all possible complexities in the distributed computing, in the randomized local model. Okay, so these are the trivial problems. Then there are these problems like vertex forecoloring. So this is on grids. Okay, maybe you should have stressed it on grids. So these are trivial problems. Then you have this class log star n. And so this class has like a different characterization. So these are problems that can be solved by a constant round algorithm, but you first need to construct a proper vertex distance coloring for some distance that depends on the problem. But example is vertex for coloring. So this is important class, and then this is it. So and then the class where vertices have to see that they have to see the whole grid. So this is, for example, this 3 coloring, and maybe then there are these problems like 2 coloring that don't even admit solution on every torus or something. Okay. And also, if you just cross out this R and consider the deterministic complexities, then it will be the same. So there is some derandomization result on grids. So this is again on grids. That says that basically randomized and deterministic classes are the same. Yeah, but I decided to talk about randomized because of what will follow now, the random processes. Okay. So it seems that this classification is complete, and the question is if this is it. But the answer is that this is not. The classification is complete in the local model. And now I would like to talk about this vertex 3 coloring and to basically show you how when you enrich basically your language and talk about infinite structures, which is in this case this infinite d-dimensional grid, then you can define effective algorithm that produces 3 coloring. So in this, like in this world of factors of IID, this 3 coloring is not global problem. It will be solvable by some efficient procedure. Okay. So now I will define this algorithm, and as I said, it should be also local in some sense. Okay. So what is the important thing? So now let's work on infinite grid. Okay. So let's work on infinite grid. And consider that we are able to do this hierarchical decomposition of the grid. Okay, so this is ZD. This is the infinite grid. And now you consider that you have some cells of different like they are assigned some number that tells you in what layer of the hierarchy they are. So we have like one cells. So these are just like this. Then some of them are merged like this. I don't know. So this will be like the second layer of the hierarchy. Then we have some third layer of the hierarchy, which might look like this, etc., etc. So these are these cells. They are just finite subset of Z to the D, and in the end, you will cover the whole ZD with these cells. So this will be like hierarchy that grows, and in the end, you will cover everything. And the important thing is that you can think of these cells as like connected subgraphs. And the important thing is that the boundary of each even if one is like the superset of the other, is uniformly, they are uniformly separated, these boundaries. So there exists some number q such that the boundaries are q apart. Okay, so like these boundaries and this also, even though on this picture, so they are not touching here. So they are not touching here. They are q apart for some number q. Okay, so once again, so what is this hierarchical structure? So these are just some. So if you have some set in here, then A is some finite subset of Z to the D. Then you know that for every V, in Z to the D, there exists some A such that V is contained in A. And then you also know that for every A and B, the boundaries are far away. So if A is not equal to B. So we have some hierarchy of subsets, and this last condition is very important. So assume that you have something like this, and now how you would how you would define like three coloring. Okay, so basically the thing is, okay, so these are like the cells in the layer 1, then these are in the layer 2, right? And this is in layer 3, etc. So what you do, so like assume that you are a vertex in some cell, so like vertex in here, for example, and now you want to color yourself. So because this set is finite, you can just consider like two coloring of this finite, let's say, connected set by blue and red. But you have to take into account what happened before, like because the cells before, they also did some two coloring on themselves. Yeah, but like these two colorings might not be compatible, as you can see on here. Like these two red dots, they are not compatible in any two coloring of the bigger cell, because they are not in the same parity of the in the same part of the bipartition of the grid, right? Well, but then you have this third color that you can use as like to basically change the parity. So here you see that I use the green color to change the parity around this right vertex, and then everything works. So the same thing when you go from this picture to this picture, these two are not compatible for any two coloring of the bigger cell, but you can use the green colors here to somehow change the parity. Okay, so now if you look at this picture, then you see that if I am a vertex here, some vertex here, some, I don't know, V, then if I know the cell, and I know also all the cells inside, then I can output my color, because I can compute, like, I can compute how the smaller cells, how they will choose the two coloring, how they will use this third color to change the parity, etc., etc. So in the end, if I have this hierarchy, then locally from this hierarchy, I can define a three coloring by just looking at the cell that I am contained in and computing how, knowing also what happened before, I can compute what will be my color. So then the locality of this decision will basically be the like diameter of this cell at most, like diameter of this cell will be the locality at this vertex. Okay. So this is like a three coloring algorithm, and now I claim that you can also locally construct this hierarchy, and for that I need to introduce this notion of uniform local algorithm. So this word uniform, like before I said that you have randomized algorithm, and for each n, basically you can think of it as like a completely independent sequence of randomized algorithms, that for each n you have some assignment what to do, some procedure what to do on graphs of size n. But here you will have to have a uniform one algorithm such that the outcomes somehow are connected. Okay, so yeah, so now I claim that with this, with uniform local algorithm, I can construct this structure T and consequently the 3 coloring. And so what it is. So you should think of it like this. So you have a vertex in an infinite graph, and it explores its neighborhood. And with probability 1, it will stop and output its position. So there is no dependency on the size of the graph because the graph can be infinite. Okay, so like you have an infinite graph and you have a vertex and it will explore a neighborhood, and at some point it will stop and it will say, okay, I have now enough information, I will color myself somehow. So in this previous picture here, the vertex would explore, and once it knows what is the cell that it is contained in, then it can output its color. But the cell can be really large, so it can wait really long time before it will be able to do anything. So each vertex makes its own decision when to finish. So now I said that randomized algorithm A is just some map from rooted graphs to sigma. So now the definition is basically the same, that you also say that uniform local algorithm is mapped from some rooted labeled neighborhoods to sigma. But the difference is how they are executed, these algorithms. So here you're a vertex and you explore your neighborhood, and at the first time that you see someone from the domain of A, you need to output the color according to that. Before, you knew that if we are on the graph of size n and everyone knows that we live on a torus of size n, then we will have to wait until Tn, and then we will output what according to what we see. Okay, so this is the difference between normal randomized algorithm and uniform. So in uniform, every vertex explores and then at some point answer without knowing what is the size of the graph. Okay. And now to measure the complexity, so we consider this random variable that measures what is the radius that is needed. So for each vertex, we can assign when it makes the decision. Okay. And so this is the random variable Ri, Ra, and then we can measure the complexity by some function that just assigns to some epsilon some positive real number, but you can think of it as actually like an integer. And now you just ask, what is the probability? What is the probability that I need to look further than this f epsilon? And then you say that the complexity of this algorithm is this function f if this is at most epsilon. Okay. So again, you have a vertex, it explores neighborhood, and at some point it will stop and output some color. And the complexity is measured by like what is the radius that is needed. So you just ask, what is the probability that I need to look further than, I don't know, 15, and then this must be at most this f, like this inverse of f applied on 15 or something. Mm-hmm. And so similarly, we can say that some LCL problem is in this complexity class if there is a uniform local algorithm that satisfies this equation and produces pi coloring, and now with probability 1, so there will be no like the error can be on measure 0 set. Okay. So but now you can ask, so this was for infinite graph. So what will happen? Basically, what is the connection between this uniform and non-uniform algorithms, and what will happen if we apply this 3 coloring algorithm on finite torus. So why does it fail? Well, because I have a vertex and I explore, and at some point I see the whole torus. But this algorithm, it will not tell me what to do if I see the whole torus. It always expects to see bigger and bigger just neighborhoods of a vertex in the infinite grid. So what will actually happen is that for this algorithm, like a lot of vertices would have to see the whole grid, and you can actually compute this. So there is this standard construction of this hierarchy when you use Voronoi cells, and it behaves like this, that the probability that you need to look further than 1 over epsilon. So when you should think of epsilon as like 1 over n, or maybe 1 over dth root of n. Then this is like the bound on the standard construction, and so the same thing also holds for this 3 coloring, because once you have this hierarchy, you can easily construct the 3 coloring, and this is like an optimal bound. So if you by any algorithm manage to solve 3 coloring on this infinite grid, then you will have to have like this bound on the decay of the coding radius. So people call this also coding radius of the algorithm. Okay, but now if you just put some n or dth root of n in this formula, then you will see that the expected number of vertices that have to see the whole torus in basically any like in any modification of this algorithm on finite grids, this will be the fraction or the number of vertices that have to see the whole torus. Okay, so like now we know that, like now we have some quantitative bound on any possible algorithm that solves this problem on finite torus. Okay, so now like some formal connection. Like what happens with the when this coding radius actually the tail decay is very fast. So if a lot of vertices finish quickly, then we can actually use just union bound and get the corresponding normal randomized complexity. Okay, so like one easy claim is that if you give me this uniform local algorithm, so it works on infinite grids. But the complexity, uniform complexity is this. So basically, now you can run it on finite torus, but not many vertices would have to see the whole torus to output the solution. So many vertices will actually know what to do, because this algorithm will tell you what to do only if you don't see the whole torus. Then you can actually get that this randomized complexity is little of the root of n, and this is somehow equivalent to this log star by this classification result. Okay, so basically, if you give me uniform local algorithm with this complexity, and you run it on finite graphs, then you will obtain the complexity of this log star. Okay, and yes, so the proof goes by some union bound, that if you just consider what is the probability of the event that you cannot output anything, then it will be so small that then by some union bound you can avoid all these events. Okay. So now what I just said is that if you give me a uniform algorithm, then you can interpret it as non-uniform. But like what about the other direction? If you give me a uniform algorithm and you know what is its normal complexity, then actually no, sorry. So what I mean here is that you have this complexity log star. This is this important non-trivial complexity class, and there is a result of Holroyd, Schramm, and Wilson that the linear algorithm actually can be found in this uniform way. So whatever is in this class R local is actually in this class U local with this complexity log star. Okay, so whenever you have a problem in this R local log star n class, then you can find a uniform algorithm of this complexity that also solve it. So these two classes are the same. Okay. So basically what I try to describe is that there is like some traditional approach when you work with finite graphs. You have randomized local algorithms, and then there is like some uniform version of it that actually makes more sense to consider on infinite graphs. But in this when you restrict yourself to this non-trivial locality, this log star, then these two models are actually the same. But you can get more information about local problems because, for example, of this three coloring. So you have some like now quantitative bound, exact quantitative bound on how difficult it is to solve this problem, while this R local model only tells you that it is global. Okay, but like to state once again what are the differences. So in this uniform model, everyone has to finish with probability 1 when you run it on infinite graph, and the solution is always, or with probability 1, it is correct. But in this standard randomized model, there are some numbers Tn, and the algorithms are basically independent for each size of the graph, and you are allowed to have some error probability. And as I said, these two are trivially the same, and these two you can prove using the result of Holroyd, Sharman, Wilson that this is actually, these two classes are also the same. And but now you get this example of some problem that is global in this sense, but you can bound the complexity here. And so the question is if there are any other complexity classes, and the answer is yes. And so now maybe looks like a bit messy, but basically for each j between the dimension -1 and 1, you can find some local problem that has this complexity jth root of 1/epsilon. So before all these problems were global and you cannot distinguish, but now you have like here and here basically different examples. Or I mean, if j is 1, then this is this. Then this is this. Okay, so this gives you like this much finer scale how you can measure complexity of problems. So yeah, so these are the, so I erased this R because the deterministic and randomized is the same for grades. So this again is for grades. Yeah, so okay, so this is the log star, this is the non-trivial class, this is the trivial class, and then there is some speed up theorem that there is nothing in between. And by just this translation between uniform and normal algorithms, you can just prove that there is also nothing in between in here. Okay, so there is also nothing between, there is also some speed up. And like how do you do it is that you just assume that there is some problem in between, and then you just take it here, and then you have speed up down, and then you so like the same, basically this down here on this bottom part, the complexity classes are the same, but then there are these more classes up here where you can, like for each j, so recall that j is between 1 and b minus 1, you can find some problems. And if you are just little o of this, then you will, again, there is some speed up to this log star. So yes, so this is like what we know, but like we don't, for example, know if between j and j plus 1 you also have some speed up or not. Okay, but like this is like the big picture that you can get just by some like simple translation between these two models. And just like once again to sum up what happens, so you have like this random processes approach when you work with infinite graphs, and you have a much stronger notion of local algorithm. It has to be uniform. And then you have this distributed computing, and you have like developed some speed up techniques or de-randomization techniques. and you have complete classification of all possible complexity classes. And now the thing is that if you put these two together, if you find the dictionary between, then not only that you can like solve some problem, in this case in random processes, because the techniques are more developed for this type of problems in distributed computing, but you can in the end get some finer scale of complexity classes. And you somehow better understand the global problems, because before you just know that they were global, now you have some quantitative distinction between them. And so now, like one more thing is that if you now combine it even with this descriptive combinatorics, you get even like bigger picture. And like what is very interesting is that this log star, this class log star, corresponds exactly to continuous to problems that admit continuous solution. And like one question is that maybe all these classes up here are the same, which would be some very abstract the randomization result. Yeah, so this is actually not known. And so let me now finish with some questions. So as I said, what in this grid context is the most interesting question is if you can get speed up between these new complexities. So basically, if you look at it like this, then there is some 0, 1, 2, up to d minus 1. And then there is, let's say, plus infinity here and 0 here. And we know that there are some problems that have complexity exactly this, all the way up to here. Then this class log star, let's say, corresponds to this, to plus infinity. And we also know that there are no problems with complexity here, because we have some speed up. If you are below d minus 1, then you have to actually be solvable by this log star. So what we do not know, what we don't know is if there are some problems with intermediate complexity here, or also if there are some problems here. Okay, so this is one thing that we don't know. And yeah, so like before this wasn't not even possible to basically state this type of problem, because now this is much finer the scale of the problems. And the randomization thing is what I mentioned here. If basically this class Borel is the same as the class factor of IID, but I didn't define what is Borel. Okay, so this is like the most important questions on grids. And then in general, on general graphs, like one question that is also very important is that we have this uniform version of linear algorithm, which is from paper of Holroyd, Schramm, and Wilson. So what they proved is that you can get this delta plus 1 coloring with tower tail decay on any graph of degree bounded by delta. And this basically gives all the result about this log star that the classes are the same. But for this Lovász local lemma distributed algorithm, it's not clear if there is some uniform version or how does that work. So somehow the algorithm that is now really takes into account that you work on a graph of size n. So you don't. Yeah. Okay, so this is it. So thank you very much.
Thank you, Jan. Any questions from the audience?
I could ask one. So could you go back to the slide where you have the factors of IID and descriptive combinatorics picture? So when you say de-randomization, I guess you mean you have an FIID algorithm to solve a problem, and you're trying to prove that there is always a Borel solution.
Yes, exactly. Yes. Mm-hmm.
So, and by Borel solution, you mean, I guess you have a a Borel graph, and you want to find, let's say, a 3 coloring that is Borel.
Yes, yes, exactly that. Yes. So I mean, there are some like canonical graphs that if you have a Borel graph that looks like a grid, then it can be like mapped inside like the general, like the inside like this shift graph. And so basically what I'm saying is that there is some object that if you solve your problem on this object in a Borel way, then you can solve it in a Borel way on any other graph that locally looks like grid, for example. So
okay, do you have also something in the converse, so problems that you know how to solve in a Borel way, but you don't know how to, do they also give you a uniform randomized algorithm?
so what we know is that like every problem that we know and that admits solution in any class that you can see actually admits this solution which we call toast, and toast is nothing else than this hierarchy. So that you have this cell process, and then you just have this assignment that have you this rule that if you know how to solve it on smaller cells, then you can always extend to a bigger cell and to a bigger cell. So basically, if you give me any like now, every problem that we know that can be solved by any means of this, like in this picture, it actually admits this solution with these cells.
Okay, but it's not a general result that says that for every.
No, it's not. But like this like I mean, I'm just saying that we are so limited that we cannot distinguish. Like it actually is possible that even this is actually one class. This could be also possible. Yeah, so we cannot here we cannot distinguish in this green box. We cannot distinguish any two classes. Mm-hmm.
Okay, I'll let other people ask if there are questions. Thank you very much.
Any more questions? Okay, so let's thank. Oh.
So nobody else is asking. How about other graphs? So you only spoke about grids today. How why and what is known on other graphs?
So why grids? Well, so the main reason was that when we just started to talk with Vasek about like these possible connections, then there is this paper of people in distributed computing about grids. Then there is this paper of Holroyd, Schramm, and Wilson about grids. And then there is this 100-page paper about continuous combinatorics on grids. And the results were exactly the same, like that 3 coloring is not possible and 4 coloring is possible. So this was like the first main motivation was to understand like why there are 3 papers and basically not just one or like something like that. And I think like this picture is already like complicated enough. But what else we have is like on trees. So the irregular delta regular trees. So then the picture is slightly different. And then there are some like general results for general graphs. So 2 results that I actually would like to discuss at this mini course is that for any Cayley graph of any finitely generated group, this class continues is the same as this log star is the same as this. So for any Cayley graph, you got that these 3 complexity classes are the same. And then, so this is a result of Anton Bernstein. And then another result of Anton is that like Lova's local lemma can be solved in this class measure and bear. And somehow it very much uses the Lova's local lemma distributed algorithm. But here on this picture for grids, you don't see the Lova's local lemma because it is basically here. It's the randomization. Like it will not play any role. But on trees, you already see some extra class which correspond to Lova's local lemma. And Anton proved that no matter what your graph is, if it's bounded degree, then this implies if you have this if it falls into the complexity class of Lova's local lemma, then you can find a measurable or bare measurable solution. And then result of András, Oleg, Lukáš, and some other people that I don't remember, they found like on sub-exponential growth graphs also that Lova's local lemma implies, but this time Borel solution. So these are like, I think all the general results that I know. Like we worked on grids and trees, and then there are these like 3 abstract results.
Thank you very much.
Okay, so let's thank Jan again, and yeah, see you all next week. Bye bye, everyone.
Bye.
Bye.
Thank you.